Okay, so I will be giving an update on Femtocode, which is about querying HEP data. So page 2, and I'll see when it updates. Okay. So I'm going to start with a reminder of the motivation, because the last time that I presented this here was December 12th, which was 4 months ago almost. So first, this is about query systems. In some industries, I've noticed that it's commonplace to query very large data sets, and I need to quantify that to sometimes like petabytes of data, in real time, usually using SQL. And there are a number of tools on the market for this. There isn't one that has taken over everything, but several different ones vying for a position, like IBIS, Impala, Kudu, Drill, and some of them are merging, and I'm kind of confused about where they all stand on that. But anyway, this is becoming a common technique. Page 3. For us, this would mean being able to do final analysis directly on collaboration shared analysis object data sets, or AODs, whatever that means in different collaborations, without managing private skims, which would be a huge advantage. You could start plotting and start doing analysis right away. You wouldn't have to spend a week skimming and then find out there's something wrong with your skim. Page 4. However, I've looked into this. This was actually one of the first things that I was thinking about when I joined Diana. I was looking at Impala. These systems don't deal well with rich objects, the kinds that we have in our AODs, like arbitrary length lists of jets containing tracks, containing hits, you know, basically like C++ objects. It really can't. You can store them in an SQL table, but the SQL commands for dealing with these are not rich enough. Page 5. So I'm developing a query system like these, whose performance would permit real-time analysis, and yet is capable of complex manipulations, the kinds of things we need to do, such as filtering tracks or picking pairs to compute invariant masses and such like that. So considerably opening up the set of operations you can perform. Page 6. So this project has 3 interrelated parts, and instead of developing one of them fully and then not having anything on the other 2, I've been jumping back and forth between these, bringing them all up to speed at the same time, so that any design decisions I learned from one can feed back into the others. So the 3 parts are the language compiler, the execution engine, and the distributed server. So the language compiler should be as familiar as possible to the user, you know, try to make it look like vanilla Python mostly. So there should be objects and nested loops and such. But it should be constrained, so not full Python, constrained to allow for restructuring of objects, constrained to allow us to restructure the code for fast execution. So total functions, map filter reduce instead of for loops. And another thing that is unique to this project, as far as I can tell, is some extra strength type system to eliminate runtime errors. So if a piece of code compiles, it should run. The execution engine operates on contiguous columns of data rather than objects, which is also an unusual thing. It's common for us to store data in columns, like root split mode, but not to actually perform the computations on the columns of data. So then when in the high-level language, when you're restructuring objects, what actually happens at low level is you're changing arrays of integers into other arrays of integers. This execution engine also has no memory allocation at runtime, and the loops are in principle vectorizable. It's JIT compiled. The CPU is a target for now, but the structure is right for GPUs. Then the third part of yeah, sure.
When you talk about the contiguous part, should I think of, you know, if you have, for instance, variable length lists of, you know, jets or something, and the jets have, say, PT, should I think of like, I mean, should I be thinking about operating on, for instance, like the PT column of the the highest PT jet or something like that, or should yeah, and
well, actually, all of them.
or all of the jets. That's what I was going to ask.
Yeah, I think your question will be answered with the details that I get into later in the talk. So, but yeah, that is the right idea in mind. The code will look like we're operating on individual events, but actually we're going to be operating on all the jet PTs at once, then all the jet ADAs, then all the muon PTs, etc.
Okay.
Actually, a mix of those, trying to balance performance. Then the third part of this is the distributed server, and I'm imagining this sort of like a vending machine. Queries go in and histograms and such come out. It's not something where we want the users to. It's not like a library or an ecosystem where we want users to dig into the methods and pull out various things. So like a vending machine, it has to work. A vending machine that takes your money and doesn't give you a snack is terrible. But I think we want this kind of closed-off interface for people to be productive with it. Another thing about this distributed server is that this language has perfect referential transparency, and that allows us, and we can use that fact, part of this cross-pollination, use this fact to eliminate the need of tracking users. And I'll talk about that right at the end of this talk. Page 7. So first I'll talk about some language compiler aspects. This is most of what I talked about on December 12th. Page 8. I'm going to start with a working example. And to make it an interesting working example, I computed the dimuon mass of Z's. And in order to do that, I had to cram a lot of code onto the screen. I do it in a very pedestrian way. So just to walk through this, we'll start at the top of the screen. We start with some session, ask for a data source. This is real data. Well, it's real Monte Carlo data, ZZ, Pythia 8. And then we just apply a chain of operations to it, which in this case is just 2. The first defines a constant, mu mass, and the second computes in a loop over pairs of muons, computes the P1x, P1y, P1z, and E of the first one, and then the second one, and then combines them in the normal way, and then computes an invariant mass. And now down at the bottom of the screen, .submit, submitting it to whatever execution engine is going to take care of it. And that's asynchronous. So then the last line is final equals pending.await, and that will block until it's done. And yes, we see the Z peak. So, this is a success already. Page 9, I'm going to get into this in more detail. Couldn't all fit on one slide. So taking this example apart on page 9. First thing you want to notice is that the Femtocode always appears in quotes, kind of like SQL. It's a big data aggregation step that feeds into a traditional analysis. So I'm not proposing this Femtocode language as the new language that everybody should use instead of Python or instead of C++. That would be too big of a task. This is really just a query language for filling objects that you're going to analyze in Python or in roots in the normal way. Second thing to notice is that one query is a workflow from source to aggregation, a rather structured thing. You start with some source, define this, define that, histogrammer, something at the end, and all of that whole chain is compiled and submitted as one unit. So that's what a query is. And then the third thing to notice is that these Femtocode snippets, with the exception of the actual example I gave on the previous page, they would usually be rather small. So that's where the femto comes from. They would usually be little quoted segments scattered throughout a histogrammer aggregation. So after making some definitions, we could imagine building a histogrammer tree where we're making a whole lot of plots out of that. Dimuon.mass, dimuon.pt, dimuon.eta. And all of these quoted segments, each one of them is a little bit of histogrammer code in the same context with the big block. Now, this wasn't in my example because I don't have this part yet. Histogrammer is not yet integrated into Femtocode. Page 10. More taking this example apart. I made a loop over pairs of muons by nesting the map functional. It looks a little bit ugly, but actually it's the only functional that I've implemented yet, so that's what I'm using. So I said muons.map, and then give it a function. Muon goes to muons.map, give it a function. Mu2 goes to some function on mu1 and mu2. This is equivalent to the following Python, doing a doubly nested for loop. Now, this is not the best choice. There will someday be more convenient forms, like pairs would have been a better choice for this, and pairs would be something that would go over just unique pairs of muons, so you're not putting the same pair in twice, as I am in this example. Table for making like a Cartesian grid over a number of different inputs. Filter, flatten, flat map, zip, you can guess what all of these would do, but they're just not there yet. Page 11. Another thing to notice about this example is that the type system requires the domain of square roots to be guarded. On December 12th, I was showing some examples with division by 0. It wouldn't let you divide by 0 because there could be, it wouldn't let you divide by a variable that could sometimes be 0, because that would allow for runtime errors. Same thing here. You just give an arbitrary expression to square root, and it will complain that it could be negative. So actually, if I put this expression, square root of e squared minus px squared minus py squared minus pz squared, directly into Femtocode, it will complain that square root of a real valued number is not allowed. It wants a square root of reals on the interval from 0 to infinity. So, and so that's the actual error message it gives you. It says line 19 is no good. So to resolve this compile time error, we put the square root inside of an if block to guarantee that the argument to the square root is non-negative, and then it's happy. And since the alternate I'm giving it in this case is none, the output type is actually going to be real or null, or none. So the compiler tracks every sub-expression's interval of validity. The if expression limits that expression to real from 0 to infinity. Actually, I said it wrong. It'll go from real from 0 to almost infinity. It'll be an open interval. Now, this for this case specifically, because of the previous steps, algebraically, this can never be 0. So in the future, we could bring SymPy into this to actually put all of these expressions into some canonical form and let it algebraically discover that. But for now, the symbolic algebra is fairly simple. Also, we don't always want to have a SymPy dependency. Okay, page 12. Now, yet another thing to notice about this example is that I put the first two stanzas. The first one depends only on mu1, and the second depends only on mu2. I put all of that inside of the doubly nested loop. Page 13. First, for people who have been programming for a while, this would raise alarm bells that those expressions are going to be unnecessarily computed over and over. In most compilers, at least one of those two stanzas would be needlessly computed for every pair of muons, rather than just every muon, as it could be. We have learned to move these expressions out of the loop, although possibly at the expense of readability. I would argue that if I had tried to restructure this so that they were outside of the loop, it would be less readable. Now, Femtocode's compiler turns every loop over objects into vectorized functions on individual fields, which I'll get more into in the execution engine part of this talk. A byproduct of this is that functions depending on only mu1 or only mu2 decouple from the functions depending on both. And so they're automatically put into different loops. We can write it inside the doubly nested loop, and it will execute outside because it doesn't need to be inside. In fact, it goes broader than this. In fact, all duplicate sub-expressions are computed exactly once. You remember when I put the e squared minus px squared minus py squared minus pz squared, and I just copy-pasted that as a bad physicist technique? This actually doesn't get computed multiple times. It'll get computed only once. So the only reason to use assignment is for clarity. So we really should be thinking this not so much as it's very high level. It's more like an executable whiteboard than literal code. Page 14. I'm now moving on to the execution engine to show how some of this happens. Page 15 shows what this dimuon example looks like after it has been Femtocode compiled, as opposed to machine code compiled. So all of my Python code looks at the Femtocode example that was given and turns those expressions into a series of statements with minimal recomputation. And in this case, you need 35 statements to do the previous thing. And each one of these statements does exactly one function. I have them, I had to make up a notation for this, so the notation is unfamiliar. But all of these things starting with a hash are temporary variables. The muons-pt, phi, eta, and muons at size, these are all the input columns. These are all input arrays, not objects. And all of the quantities that start with a hash are, at least conceptually, also big arrays of values. But I'll show on the next few pages that they don't necessarily need to be actual arrays. And
is it assuming here that like muons pt and muons phi and eta all have the same? This muon, they all have the same size, just so this is implicit in your muons bracket.
That's right. Yep. In fact, that's what the little headings that I've added, sized by this, sized by that. That's what I'm expressing there. That the first 11 statements all are associated with the muons at size array. And then the rest of the statements are all associated with the hash 11 at size array that has to get created at runtime. Yeah, and that'll be a key part of all this. Yeah. Page 16. So, okay, now starting with that series of statements, each one of those statements was a vector statement. It was, you take a big array of this and you can get a big array of that out. Now, we have freedom at this point to choose the looping structure, more so than an ordinary compiler. I'm pretty sure that there aren't any compilers that do what I'm about to say. So suppose that we have a dependency graph like this as an illustration. We are free, and each one of these nodes in this dependency graph are vector statements. We are free to choose where to put the loops in order to implement these vector statements. Page 17. We could imagine making each one of these steps a loop, kind of like what NumPy does if you're doing a bunch of NumPy statements in Python. We could imagine, in order to make T0, we loop over all of the A's and B's before moving on to the next. Page 18, we could imagine doing everything in one big loop. And then T1 through T8 are all scalars. You don't get another array again until you get to T9. Page 19 shows an intermediate case where we could make two loops, and then only the quantities at the boundary between the loops have to be arrays. So note that making this choice of where to put the loops changes which quantities are arrays and which are scalars. Now, we have that freedom should we use it. Page 20, what are the trade-offs? Why would we put a loop around every individual statement or as big as possible or somewhere in between? So assuming that the bottleneck is memory bandwidth, and this is usually true in all of the performance optimizations that I've been working through, memory bandwidth matters more than anything else. I guess it's because I'm always doing very simple operations. So assuming that the bottleneck is memory bandwidth, more loops increases the number of memory passes, which is bad, but sometimes decreases the number of arrays that you need to stride simultaneously. And this can be good because the CPU is trying to prefetch this memory, and you could imagine if you were looking at hundreds of memory locations at once, it's not going to be able to prefetch all of them. So I did a test to try to find out if there's a sweet spot. I split one loop over 64 variables into 64 loops over one variable each and everything in between. And I see that on most architectures, one is usually pretty bad. And when you get up to 64, it gets bad again. But there's a very low, wide sweet spot from 2 to 32. And since I don't expect many queries to be using more than 32 inputs, I'm going to try to make these loops as big as possible, at least for now. If we start seeing queries with that rely on hundreds of variables, then we would want to make the code more complicated and split them up. Page 22. Now, I was talking about the cases in which you had the freedom to choose, and I've decided to make them as big as possible. But sometimes you don't get to choose. So some vector operations have a higher cardinality than others. So for instance, a loop over jets has more steps in the loop than a loop over muons because there are more jets. Operations of different cardinality can't be put into the same loop. So Femtocode divides the dependency graph into plateaus. So if you imagine that dependency graph and now just turn it on its side, make the vertical axis the loop size. If we look at loop size versus dependency order, assuming that we had some kind of linear dependency, you would see, first some operations on each event, and then it goes up to a higher size when you loop over each muon, and then back down to loop over each event, and then up to loop over jets, and then down to one result per event. So page 22, if I were looking at an example like this, it would have to get split into 5 loops, assuming that each step strictly depends on the previous. Because if 3 and 5 don't strictly depend on 2 and 4, then they could all be combined into one loop over events. Page 23, our dimuon example splits into 2 loops. This just automatically happens by applying this the loop splitting algorithm. One of those loops is over muons at size, and the other loop is over the pairs of muons, hash 11 at size. Page 24. So then we're taking the dependency graph and finding all of the plateaus. The plateaus are made of 3 kinds of operations, and so I'm introducing a nomenclature and to be able to keep track of how we build these things. Explode operations, which you've seen some examples of in the code, it increases the cardinality of one array so that it matches another. For instance, increasing from the cardinality of muons to the cardinality of muons cross muons. This determines the indexing of the loop, so it has to be first. Then the flat operations are when you apply a function to all members of 2 aligned arrays. So we don't have to change the structure at all, ignoring event boundaries. The intermediate steps need not be arrays. So this would be the top of the plateau. You try to get as many flat operations as you can into one plateau. Incidentally, these operations are also the ones that are a perfect match for the GPU because Anyone familiar with GPO programming would see that. And then the third type, which I've not implemented, I don't have any examples, any working examples of this yet. I'm calling them implode for symmetry. It's when you combine results by summing or take the mean or a maximum, etc., to reduce the cardinality of an array. The size of the output arrays are not constrained by the indexing of the loop. So we could, from a single plateau, we could implode to several different cardinalities. But anyway, it is the last step that you can do. So after this, you're done. Page 25. So now that I've talked about how we're going to deal with a dependency graph and split loops up, how are we going to deal with the actual computation itself? So we're just going to concentrate on one loop. How do we take something where we're maintaining at high level the fiction that these muons are a collection of records with PT, eta, and phi, whereas in the reality, they are a bunch of flat arrays. Muon PTs, that's just the values without regard to any event boundaries or anything. The phis and the etas, and yes, Kyle, like you said, these three all have to have the same length, 132, 274 in this case. And then the muons at size array, which has a different length, it has the length of the number of events, 48, 131. And then the dimuon run produces some more arrays. Hash 34 is the result of the calculation, and hash 11 at size is its corresponding size array. So these are what gets output. And these have different cardinality from the inputs because they're for each pair of muons. Page 26. Well, so these size arrays, for simple collections of records, in other words, particles, they should be pretty familiar. These arrays have the same interpretation as root T-leaf counters. So the data arrays contain all the values ignoring the event boundaries, just like in root. And the size arrays contain the size of each event's collection, just like in root. So just a root T-leaf counter. But for collections of collections of a fixed known depth, this goes beyond what happens in root. We can extend the definition recursively. So given this nested structure like open bracket, ABC, close bracket, open bracket, etc., for this list of lists, we make the data array by just ignoring all the brackets and writing out the data. And we make a recursive counter by, at each open bracket, we give the size of how many objects are inside that bracket. So first, there are two. There's the list ABC and the list DEFG. And then the next item in this recursive counter is the number of elements inside the first list. There are three, A, B, and C. And then 4 for D, E, F, and G. This stores all of the information. It's lossless. You can reconstruct the original thing, the original nested object from it. And we can do computations on it, keeping track of, and we know whether the number refers to the outer collection or the inner collection by keeping a stack of countdowns. So on page 27, I show what this actually looks like so that I can refer back to this. Although I'll actually talk about what's going on this page in the following pages. This is the code that gets generated for the red Femtocode at the top of the screen. I have 3 nested maps because I want to show a rather general example. XSS is a collection of numbers. YS is a collection of numbers, and so you do 3 nested maps in order to get to the level where you're actually combining scalars. And then that generates the code below, which is really just one while loop. The second nested while loop is just for closing parentheses. So let me talk about it in more detail on page 28, where I describe it as a bulleted list rather than just showing you all the code. But you can jump back to the previous page to see how this applies. So a bunch of points to make about this. First is that this loop is JIT compiled for the specific nesting that we observe. Not only is this faster, it is actually easier. Earlier, I tried to write a completely general loop for any collection, for any kind of nesting, and it was much more difficult. This is a case in which metaprogramming actually makes things easier. Another thing to note about this is it never allocates any memory at runtime. We're not creating objects. We're just running through arrays. Yeah, and so we don't ever have to allocate anything for that. There are always two nested while loops, no matter how nested the femtocode is. The second only pops out of the stack. And I've been thinking about this, and actually, this doesn't really need to be a while loop. It could be JIT compiled if statements, because I know exactly how many of them there are. The walkthrough data is controlled by stacks of fixed depth. And in the example I showed on the previous page, I was actually writing out the stacks as arrays. But since then, I've replaced this by JIT compiled stacked variables. So instead of having a 3-index array, I actually just made 3 variables and compiled that. And it's considerably faster. Another thing about this is that the memory access pattern is contiguous and usually forward, which I know from my reading is a good thing for CPUs to be able to prefetch. Though it sometimes has to jump backward to emulate loops. You know, for instance, if we do our example, muons.map mu1, muons.map mu2, the second index over the second muons, it has to, of course, jump back because it's actually filling out a table. So I think I'm seeing some hints that this is ruining performance. And I need to investigate that more. I also have an open question that I haven't answered for myself, which is I've written all of this using a single loop and stacks of indices. Would a version using recursion be faster? And it's possible that it would, because maybe the LLVM compiler would have a better idea of what to do with it. Maybe the instructions that the CPU sees, it would be able to inspect them better. I don't know. I should try that at some point. And the last thing about this is that I'm actually generating Python code, like you saw on the previous page, even though we're compiling it to machine code using Numba, which uses LLVM. And this has been great for testing, because if I get any index errors, Python tells me about them right away, whereas when I'm running native code, it's a segmentation fault. So I like this way of going about things. I'm writing Python that almost looks like assembly code, and then it compiles down to something fast. Page 29. So why do we even do this? Why not just create runtime objects like C++ classes? The first point was to try to help LLVM, or try to help the native compiler, and the CPU hardware optimize memory bandwidth, because that's the most important bottleneck. To show examples of how this matters, I took a loop over JetPT values and did something very simple to them. I think I multiplied them all by 2 or squared them or something. Something that's depends only on memory bandwidth. A no-frills loop in C, you can't get any faster than that. It's 3 milliseconds. Next step up, NumPy is almost a no-frills loop in C, 7 milliseconds. The event loop I showed on the previous page is 14 milliseconds. I'm kind of unhappy about that. Really, this should be down to 3. But now the point I wanted to make with this table is that if you're actually allocating C++ objects and even compiling with the -03 flag, it'll take 24 or 64 milliseconds to do this, depending on whether you allocate them on the stack or on the heap. When you allocate them on the heap, you additionally have to delete them. And then beyond that, if you go to do normal things like TT-draw or a CMSSW analyzer, it gets even more. But they're doing more work, especially CMSSW. It's doing a lot more disk access. So this is why we want the actual execution engine to not deal with objects, but to deal with plain arrays. Page 30 is another reason why. When we have those flat data arrays with no event boundaries in them, the flat functions at the top of the plateau perfectly satisfy the criteria for GPU acceleration. So when all that is implemented, we would have a way to automatically translate high-level physics code on physics objects into not just into GPU kernels, but into well-optimized GPU kernels. And I think that would be a big deal. So 2 reasons for trying to do everything with arrays rather than objects. Page 31, the last thing I want to say about is that it is not a closed down sandbox where you can only use the functions that I create. I'm trying to make this open-ended so that new functions can be added. Here's an example where we're actually running a root function in Femtocode. And I wrote out everything you need to do to make this happen. The first block is in some library that the Femtocode server can see, where we find the root function not by using import roots, but by using Python's C types. So Python knows about the location of this in the foreign function interface, and then we have to set the argument types for it to be able to call it properly. And then on the client side, the second block, we have to wrap this function with a Femtocode-friendly signature. So for instance, this is a chi-squared quantile function. The first argument has to be a number, and it has to be between 0 and 1. So I wrote some assertions asking for that. The second has to be a whole number, because it's a number of degrees of freedom. So I wrote an assertion for that. And then the output is a non-negative real. So I return that. So this chi2 sig is telling Femtocode what's allowed to go into this function so that you can use Femtocode's type safety to eliminate runtime errors. And of course, this is all on your honor. You have to write that signature correctly. But then you can load this, this function and its signature into a custom library. And the very bottom of this is testing it out. I'm using it in Femtocode. I'm running it in a native test session, so it's being compiled to native code. And when it's being executed, Python is completely not involved. So even though we access this chi-squared quantile function through Python, it gets entirely compiled into the ELF, into the bytecode. Python is not a roadblock in using that at all. Okay, so the last topic, page 32, is the distributed server. Page 33. So now that I've talked about just being able to run anything at all, we need to be able to scale up to full data sets. So let me take a step back and think about what is the, back to the goal of this project. We want this to be usable in exploratory data analysis. And to do that, you need turnaround times on human timescales, like seconds at most. In order for a data analyst to investigate something, they need to have this back and forth conversation that happens, without having to go get a cup of coffee. So if a query server takes much longer than a few seconds, physicists will just go back to private skims because it would be the only way they could be productive. So is this possible? Is it possible to reach that level of performance? Well, so let's do some scaling estimates for one query. Typically, a query might invoke a dozen or so samples. Let's say that we're making a backgrounds plot and we want to draw all the different background samples adding up to the data. And I've noticed that in many analyses, this is on the order of 10 terabytes, very roughly. Now, every query should run over all events. Otherwise, the plot you make won't be, describing like all the 2016 data. But a single query rarely uses more than 1% of the columns. The population distribution on columns is very steep. Many of those variables in that 10 terabytes is isolation variables with different cone sizes and such, and JET algorithms with different cone sizes that not everybody uses. And certainly nobody uses them all the time. So really you're just dealing with, say, 100 gigabytes at a time. In this very early implementation of Femtocode, the worst query response times on reasonable queries, which was a loop over pairs of jets, were 30 milliseconds per megabyte. So if you multiply everything together, you get 3,000 core seconds for this query, 3 seconds for 1,000 cores, which is in the ballpark. This is a good start. Page 34. Now, what about scaling up to full collaboration? So we've got multiple users hitting the system at the same time. First, I'm going to argue that this is actually a good thing. So most analyses have significantly overlapping needs. To take as evidence for this, I'm going to cite the fact that I've looked at a few of these homegrown skimming frameworks, Bacon, Pandas, CMS3, TreeMaker, all of them are inside CMS. And they all select the same 10% of CMS mini AOD. So most people don't even need all of mini AOD. They do all of their analysis with at most 10% of it. Second point in this argument is that the file I/O is much more expensive than processing. So 40 milliseconds per megabyte for file I/O versus at best 2 milliseconds per megabyte for processing. So taking those 2 points together, everybody wins if the users share cache, because most users are going to be wanting to look at the same input data. So now 10% of 10 terabytes of samples is 1 terabyte, and that easily fits into the RAM of a 1,000 core cluster. It would be hard to fit on one user's machine, but you see the sharing really helps in this case. Now, those are all reasons why it would be good to have multiple users on the same system. Why would it be bad? Well, they might all be submitting queries at the same time, and there would be contention for resources. Well, this is actually kind of hard to estimate. I've been thinking about this, trying to figure out how to estimate this. When you have a normal batch system where each user's process takes a long time, like hours at least, well, they're usually overlapping each other. And so usually you're having to deal with many at the same time. In this case, we want the queries to be very short-lived. We want them to be, seconds or less. We actually have they have a different scattering cross-section, right? They are less likely to collide the smaller they are. So trying to figure out how much contention a system would have like this depends strongly on its latency, and we're trying to minimize that too. So I don't know, maybe one should always design the hardware so that so that two of these 3-second queries rarely hit each other at the same time. Maybe. And of course, all of that depends on what hardware you allocate for it. And all I can talk about right now, since we're nowhere near talking about making a real system, is improving the software to steepen the performance per price. So that's all I'll talk about from this point on. Page 35. So to try to make a scaling formula for this, remember that Femtocode's design philosophy is to do work up front in order to streamline the event loop, because the idea is that the number of events is the one big number in this problem. In a distributed server, managing subtasks is also part of this upfront work. So I'll write a scaling formula like this. The time to completion is some constant C1 that's dominated by 70 milliseconds of JIT compilation time. Some function C2, function of the number of cores. This is the overhead, the time spent managing subtasks, and this is all written in Python. It is a complex concurrent process with some locking involved. It is affected by Amdahl's law, so I expect that C2 function to be one of these Amdahl's law curves. And that's multiplying by the number of subtasks, the number of partitions the data is partitioned into. C3 is the part that actually executes the user's query. This is different. This is both natively compiled and embarrassingly parallel. We have the freedom to divide this up however we like. So here I'm just going to assert that it is embarrassingly parallel, and it's an extreme limit of Amdahl's law. We can really say C3 divided by n cores times n events. So the order parameter in all of this is n events. We don't get to choose that, and it's big. We do get to choose n subtasks over n events. So if we have a problem with C2, this overhead, this data management, we can just make the partitions larger, up to a point, of course. Page 36. So I do have a distributed system. It does work. I've been able to run some queries through it, but I haven't done any large-scale testing. This is an overview of what it looks like. This is the schematic diagram. The client is on one side of the wall, and it only talks to this one kind of node called dispatch. And behind that, there are nodes that actually do the computations. There are nodes for storing partial results. There are nodes for managing metadata, and a node for DataDB. And this ball here, this DataDB, could actually be EOS or root. So those are all of the pieces. Page 37. There is a lot that I could say about the design of this system. I struggled last night to think of what are just a few of the most interesting points. One of these points is that you should, if you're thinking about this kind of like a batch system, because, well, it does take a job and scatters it to the compute nodes, and then they run in parallel and it gathers. You might be thinking of it like a batch system, but it's really different. And here's some reasons why. First, there's no need to have a job ID or even attempt to send results back to the user. And that's because, remember, Femtocode has this perfect referential transparency. So if you write the same code on the same data set, you will always get back the same result. So identical queries on the same data set, you could actually identify the job not by some unique integer, but as a hash of the query itself. Then that way, we can have a client that only polls for updates and can even break or reestablish connection, or they can reboot their laptop or whatever, and still get the result back. So that's the reason for this storage node. When a query has been solved, the result goes into this stored database, and dispatch looks there first. So maybe I'm getting too much into the weeds trying to describe how this works. Really, the upshot of this is that when users refresh their analysis scripts or run tutorial examples, they're not stressing the computation engine. There should be no cost associated to, oh, let me just run my script again, and it submits a whole bunch of queries to the server. Well, that's okay. The server has those cached. The second way in which this is different from a batch system is that the subtasks are not randomly assigned to compute nodes. They are assigned based on what data they need, a hash of the input column names. This is because the caching is very important, and we want the jobs to go where other jobs that requested the same input data have already gone, so that the cached input will already be local to that node. Page 38. Some more things to say about this is it's very loosely coupled and resistant to failure. So each circle on the diagram is a collection of identical nodes, and none of which is a single point of failure. So for instance, if a compute node disappears, the hash assignment function has a series of fallbacks. The dispatch nodes are stateless. They can die and be rebooted. It's fine. They can be load balanced. Only the store, that one ball, persistently holds results. And so therefore, I did not write it. It's a MongoDB instance with appropriate partitioning and replication. Holding a persistent state in a distributed system is a hard problem, so I'm using some off-the-shelf tools for that. The data sets in MetaDB and DataDB are treated as immutable artifacts. So new data sets can be created with version numbers, but they can't be changed in place. So finally, I'm going to just get to the conclusions, page 40. Progress on all three aspects of Femtocode query server projects, the language compiler, the execution engine, the distributed server. I've been bringing all of them up to speed at the same time. The language compiler is starting to compute meaningful quantities. The parser and type checker are mature. It's really a matter of just loading it up with a bunch of functions and doing the complex things like explosions and implosions. The execution engine, this problem of how to solve general explosions is under control. That was a real problem for a while, trying to figure out mathematically how to solve it. Compiling with LLVM works, and even serializing compiled functions for remote execution, which is needed for the distributed server, that also works. I believe it is factors of several from optimal performance, but I think we can work with this for now. The distributed server, well, I have a working prototype and it passes data through. Thought about scaling and robustness, but I haven't really tested that to see how well it scales. And the last point I want to make is that I wouldn't have said this earlier, but now I believe that this project is mature enough that we may be able to split off sub-projects if anybody's interested. If you think, wow, this is cool, I want to do some part of this, or maybe I have some new idea that I want to introduce to that, ask me and we'll talk about how to grow the developer base. So that's all I had to say. Any questions?
Great. This is Kyle. I have a couple quick questions. One, I was just wondering, simple like your dimuon example, if you want to only do this computation, say for muons that have PT bigger than 20 GeV or something like that, can you just say a little bit about what happens? I mean, are you still sort of doing this over all the muons everywhere?
Yeah. It'll need a filter function.
Right. Yeah.
But yes.
Okay. And that would be, that's something that would get cached somewhere, and then you would.
Oh no, I don't. Yeah, I've had some thoughts that in the far future we might want to cache partial results, such as filter masks. Okay. Actually, in this paradigm, this way of doing things, I don't think that skimming would actually help execution time much. The only cases in which skimming, or making the data set smaller, would help execution times is if you also repartition, which is a difficult thing to do on the fly. The reason for that is you've got all this, you've got say 100 subtasks, and you've got slow Python code managing these 100 subtasks, and there's a cost associated with each one of those 100. In the original data set, each one of those 100 is running over 1 million events, and so the CPU is spending most of its time in the C code. That's in the compiled code. That's good. Now, if you had filtered them a lot so that very, very tight cut, so that the million events goes down to 10 events per subtask, then you're going to be spending all of your time in the Python managing subtasks to do these little tiny 10 events per compiled code, and that would be not efficient at all. So I think in a lot of cases, it's going to make more sense to just run over all of the data every time. In a lot of cases.
Yeah. Yeah. So I think that, I think that's it definitely, it's possible. I mean that's something that seems like is a pretty important for trying to think through this thing about, or maybe there's some regimes where it makes sense, for some kinds of queries it makes sense, and for others less so, or something. But I think it's, I like the whole project. I think it's super interesting. I mean, the two things that I wonder about, one are if most people are making some cut that that was only then talking to a small fraction of it, like at what point do you lose that trade-off that you were just discussing? And the other one that I wonder is that, seems like there need to be some sort of protections in place for this kind of temporary store, because if people, accidentally, say like calculate the, invariant mass of all jets and all of the events at the LHC or something, that's going to be a pretty big thing to cache.
Oh yeah, I should point out a few things. So I've gone to the slide with the distributed system layout, page 36. And on your 2 points, first one, let's see, what was the first one?
That was the filtering.
Yeah, the filtering. With the filtering where we'd want to also repartition, the one arrow on this diagram that actually is not implemented is the one on the bottom right, create new tables for users to query. If, for instance, there's a standard set of Higgs cuts, and they are very deep cuts, they get rid of 99% of the data, then it would be advantageous to make a new data set called with Higgs cuts, the original data set with Higgs cuts. And so we can use this system to filter through that, but then have to do something extra to also repartition them to make the partitions large enough that subsequent analyses on that Higgs table are efficient. And that would all be something that happens inside, internally inside the system. Now the second point about filling up this store, I didn't mention it here, but any query results that come back to the user are aggregations. So they could be, they would be histogrammer aggregations. So they would be these fixed size small things like 100 numbers for the bins in a histogram. Those are the sorts of things that go into store. You don't actually put raw PTs into store. I mean, not just as a matter of policy, but as a matter of it's not programmed that way.
I see. Okay.
Now, in saying it, I'm realizing that there are some things to worry about. Like in histogrammer, there's a sparsely bin, and the memory usage of that grows with if you make your bins too fine. So yeah, we would probably need to have some protections in place for things like that.
Right.
And there's another place where we're going to need protections. When this is a production system, the client sends it Femtocode compiled code, so that list of statements. In a real production environment, we should not trust that. We should have the dispatch redo the Femtocode compilation step, because someone could be malicious with that and cause segmentation faults in our compute. Or someone has a very old version of the client and they're not computing what they think they're computing. And then this would be a service to them to warn them, oh, when I compiled this up on the server, I get a different set of statements than when you compiled it on the client, you probably want to upgrade. So there are places where we have to think about safety and protections.
Yeah. Great.
Mm-hmm.
Others?
Mm-hmm.
So Jim, a couple things. One, I mean, it's clear that a system like this could have great advantages, from the whole reproducibility game to this last thing you mentioned, which is that if you are able to recognize common queries, right, sort of over time,
yeah,
right? You know, as a reproducibility here, you know, one of the difficulties we have with reproducibility is that we wander off into the wild with user n tuples, right?
Mm-hmm.
In terms of provenance and everything else. Practical things. How do you see Ollie's there? I think, right? Hi, Ollie. You know, in some ways, this is not dissimilar to some of the things you're trying to do with the Intel project, right, Ollie? It's the same game. Ollie?
Maybe he's looking for his mute button.
I'm here. I'm sorry. Yes, it's not. It's really not different. But I mean, what is nice of Jim's approach here is that it is not based on something that already exists in industry. Right? I mean, what Intel is doing is we just take Apache Spark and try to make it work. I mean, there's no real. We're going to develop something completely new. Well, I think here that is something completely new. But maybe I'm wrong. I mean, you can correct me.
But that was one of my next questions. To what extent could this reuse anything that's out there, or Jim? At any point?
Yes. So I did a lot of thinking about that up front, about how much I can use what's already out there. And like I mentioned, for this storage component, I'm using MongoDB. For the DataDB part, this EOS, we're also developing a database, blob store-based storage, but I wanted to make sure that traditional EOS is also supported. For the most part, this is using ideas in industry, like the IBIS, Impala, Kudu, etc. Those are all different projects that are all trying to do this sort of thing, but not on data with the rich structure that HEP has. I'm trying to do I'm trying to invent as little as possible, actually. Trying to do the same sort of thing with that, but just expanding it to richly structured objects. And then I think that this would feed not just into the physics community, but into data science as well. That's why I want to present this at some of the in the industry conferences, because I think that they might just not be doing analyses, limiting the set of analyses that they consider, because they're not thinking about richly structured objects, whereas we've always had these rich structured input data. So that's your answer. Trying to reuse as much as possible, but this is mostly reusing ideas, and hopefully we'll make it both useful in both communities.
So yeah, is this what you're aiming to show at Strange Loop, or?
Mm-hmm. Yeah, that's where I hope to get some. They have a lot of language enthusiasts and distributed system enthusiasts, so this is right up their alley. I hope to get developers interested in that from there, that they would actually want to use this in their companies and develop it, so it's not just me maintaining it.
So you know what, if this system is sort of is in use for some significant part, it actually means that the back end, that whether it's EOS or root or some other technology for the data DB, we've essentially decoupled people from root, right? What it's back end is just the output of the AOD production process or whatever it's called in each experiment. But there are other reasons why people produce sort of n-tuples. One is the fast iteration time, which you're in part dealing with here, right?
Yeah.
But people also do it because for two other reasons. One is reproducibility, that they, with a smaller set of pre-calculated quantities, they can guarantee that they get the same results, right? Because they've stored them, right?
All right.
And the other reason is reliability, just by dealing with less moving pieces and typically locally on some, the output is on some smaller set of machines, that they can get a very reliable turnaround time on some subset, right?
Yeah.
At the cost of going back periodically to do these big, skim n-tuple productions every whatever, right?
Right.
So how do you think we can guarantee those two things, namely the reproducibility in a calculation sense, if you have floating point calculations out there, right? And the reliability.
Yeah. So the assumptions that I pointed out, that the data DB and the meta DB are immutable, those have to be maintained. We have a problem if people are deleting data sets. So we've got this situation now that if a collaboration centrally deletes some data sets, the data analyzers are able to keep going because they have their own private copy. This system you would eventually have to delete some old data sets, and so this doesn't address that. We could address it by, we have been thinking about, here I'm just developing this software that runs a distributed server. That doesn't mean there has to be only one of them. We've thought about smaller physics groups setting up their own small clusters and running this on it. And I was thinking of that from the point of view of they don't want to they don't want other users preempting their cache. And so that was the reason I was thinking of that. But the reason that you mentioned, that they want to absolutely control the input data and make sure that it never gets deleted until they say so, would be another reason.
So what do you see as the next steps here? I mean, it sounds like it's a couple steps away from finding an analysis and demonstrating that one can do it end to end, right?
Yes, it is. Yeah.
What are the next steps?
Probably the first user. Much as I started this whole discussion by saying, down with private skims, we're going to get rid of private skims. Probably the first user will be a private skim, running the standalone version of this, where all of these bubbles all of these bubbles happen within a single process, multi-threaded. With their skimmed root files, we'll just use those files on disk as the data DB, and help them do exploratory analysis on their data set, just as they might do exploratory analysis with T-chain. They could do it with this and then produce the root histograms. That would probably be the first user. But like you said, I am several steps away from that. What's happening immediately is just more of this general development. As I said, there are no implode functions. Well, that's the next thing. Also, I have this I keep saying that the final step of every workflow should be a histogram aggregation. Well, none of that's implemented. Kyle mentioned filtering. Yeah, filtering is important, but it's not there. My laundry list of things to do is very obvious.
You know, ultimately, if we pursue this and get some steps along, the other trick will be how it actually is set up as a system that people can use, right? And
yep.
Of course, if one can set it up as a standalone thing, or within a single process, it's completely trivial, right? But it would have the advantage, much like what we've seen with Spark, is that it's scales to running on different systems. So the same thing then could be run on a provided production system, or on a local set of data.
Yeah.
There are also several steps away from thinking about how it would be, the mechanics of actually setting it up and running on a larger cluster.
Yes, right. I should mention, to clarify that, yeah, there's several different executors within this. There are some for just running unit tests, but then there's the standalone that does everything in one process, and the distributed, which is what you're seeing on the slide. The standalone that does everything in one process it will use all of the cores on your system. So that could be, there's already value added to that. A user would be able to use this to use all the cores on their system to do some n-tuple analysis without having to set up the parallelization themselves. So that would be a way to convince users that they want to guinea pig this. They want to be guinea pigs for this.
Right. No, I mean this. This is hiding the parallelism is our primary game, right? Hiding the need to make explicit parallelism. So, do others have questions? We're sort of almost heading an hour and 15 minutes in. Anyone else have questions? What else do we have? Dan, Ali, Philippe, go ahead.
Well, I have a question I wish I asked at the beginning. Were you recording this for YouTube?
It is, yes.
Oh, good. Okay, good.
I don't have a question.
Okay.
Do you have an answer, Ali? Anyone else? Okay. So, well, thanks, Jim.
All right. Well, thanks.
Thank you.
Bye, everybody.
Okay. Thanks. Bye-bye.